Okay, now we can get started. So glad you all came out. I know it's a little bit of a bad driving day today, but good to see everyone. All right, so what did we cover this week? Anyone, or like this past week, last week? Does anyone remember? Yeah. Yeah, right. So we sort of started talking about like doing various operations with matrices, right? We did like, let's write out some of the, maybe we won't start with multiplication because that's probably the harder one. What's one of the easier stuff we can do with matrices? Anyone remember? Yeah. Sure, it's an easy one. So the transpose. So if I have a matrix, let's say 1, 2, 3, 4, 5, 6, and I take the transpose of it, put a little t above the matrix, then really what we're doing is we're swapping the rows and columns. Another way to think of it is you're like flipping the matrix or like flipping it across the diagonal. I don't know if that makes any sense to you, great. If not, yeah. So like that, right? Does that make sense? We just sort of like took it and like flipped it. What other operations do we know? Yep. Yeah, those are easy, right? So, say that I gave you the matrix, this matrix here, 2, 3, minus 1, 4, and I asked you to add 4, 5, 6, 7, 8, 9. What's the result? Sorry? Why? Exactly, right? You can only add or subtract if they're the same size, right? This one's 2 by 2, this one's 3 by 2. So yeah, you have to be the same size. What would I do if instead it was like this? Got rid of that last row. Now they're the same size. Can I add or subtract it now? Yep. So let's add it. What's the result? How do I do it? I know this might seem easy, but so I do it element-wise, right? I do 2 plus 4 is 6. 3 plus 5 is 8. 6 minus 1 is 5. 4 plus 7 is 11. That's it, right? What other operations do we know? It's another easy one. Sort of like this. It's a kind of multiplication. Scalar multiplication, right? So like, I guess this is a scalar multiplication. So the idea is like if I were to take the matrix, let's just take that one, 2, 3, minus 1, 4, and I multiply it by like, I don't know, a half, let's say, any number, doesn't really matter. Maybe I'll do negative a half just for fun. Then I'll get, so negative a half times 2 is positive, or negative 1. Negative a half times 3 is negative 3 over 2. Negative 1 times negative a half is a half. 4 times negative a half is negative 2, right? Just multiply every entry in the matrix by the number. There was one other relatively easy operation. Does anyone remember it? It should have been new to you probably, but trace, yeah. So what is the, how do I find the trace of like, let's do 1, 2, 3, 4, 5, 6. You can't, why? Has to be squared, yep. Maybe I'll add an extra column here. We'll do 7, 8, 9. Let's say this matrix here. What's the trace of that matrix? Yep. 14, right? So you're basically adding up along the main diagonal there. So it's going to be 1 plus 4 plus 9 is 14. Now, when you're seeing operations like these, one of the key things to think about is like what comes in, like what are like the inputs if you're thinking in a computer science term to the operation, and what are the outputs, right? So when we take the transpose of a matrix, we take in a matrix and we output another matrix, but the size changes, right? So maybe we take a matrix that's 3 by 2, and when you take the transpose, it'll output a matrix that's 2 by 3, right? With addition and subtraction, it takes in two matrices, right? So it takes in a matrix that's, in this case, 2 by 2. And it also takes in a matrix that's 2 by 2, so two of them. And it outputs another matrix of the same size, right? I know this seems obvious, maybe, but it's important to see this and to see what we're doing exactly. Scalar multiplication. It takes in a real number, so I'm just using R for a real number. It's like any number on the number line. And it takes in a matrix that's, in this case, 2 by 2, and it outputs a matrix of that same size. The trace takes in a matrix of any size, this case 3 by 3, has to be square, and outputs a number. So you see how each of these are different, not only in like how you calculate them, but also like what they take in and what they spit out. Does that make sense? Cool. So let's talk about, I think that's everything I want to talk about with the basic ones. Let's go on to matrix multiplication. So I'm going to erase this. All right, matrix multiplication. Can someone tell me what the requirements for the sizes in matrix multiplication is? Yeah. Yes. Same number, right? So you want to take a matrix that's, let's say, like n, or maybe I'll use different letters. Maybe it'll be like A by B. So it has A rows and B columns. And you're multiplying that by a matrix which has maybe, let's say, B by C. So you need to have like, if you write them out like that, the two that are closest to each other have to be the same number. That's kind of a way that I write it sometimes. So it has to be the same number, the two that are sort of closest to each other when you write them out in order. So that means that matrix multiplication is an operation. It's not what we would call commutative. Does anyone know what commutative means? Maybe you learned this in discrete, yeah? Yeah, in this case, order does matter, right? So it's not commutative. So like if I did A times B and those are two matrices, it's not the same thing as B times A. I can't just like flip them. With numbers, you can, right? If I did like 5 times 7, it's the same as 7 times 5, right? In this case, you can't. Does anyone know if I had these two matrices, so an A times B size matrix and a B times C, what would the result of that matrix multiplication be? Yeah.
A by C.
A by C, yeah. So matrix would be A by C. So you look at whatever's left over, right? Cool. Okay, let's do an example. I've got one here on my phone that I pulled up from Google because I'm not creative enough to come up with one. So let's say 2, 6, 4, 1, 9, 7. And we want to multiply it by 3, 2, 4, 10, 11, 8. So the first thing to check is, can we do it? Maybe what I'll do to do that is just write down the sizes of the matrices, right? And this is where like students often make mistakes, right? A lot of times students will say like the rows of this and the columns of this, right? Or maybe you write out like you flip the order as you write them out. That's very common. The way that I like to do it is, first off, you just sort of have to memorize that rows come first and then columns, right? I don't know if there's a good way to memorize that, but I'll let you figure that out. But then what I like to do is, and I do this every single time I do one of these problems, I take my hand and I like put it down. I know rows go across. I like put it down on the matrix. So I got 1 row, 2 rows, right? Sometimes people will be like, oh, rows go across, so there's 1, 2, 3 things going across. That's not right, right? It's an easy mistake to make. I always put my hand out, 1 row, 2 rows. 1 column, or 1 row, 2 row, 3 rows, right? So we know this one here is a 2 by, and then how many columns? 1, 2, 3, 3 columns. And this one's a 3 by 2, same way. They have the same sort of inner numbers here, so we can multiply them, and the result is going to be a 2 by 2. Now, one thing to notice is that when we write out a product like this, a matrix product, this is sort of being nitpicky, but like I want to make sure that you're using okay notation. We just write them, the 2 matrices next to each other. So like A, B. We don't write like A with a cross, B, like times B. We don't do that. Technically, that means something different. We don't put a dot between them. Some people put dots. That's not right either. You don't put brackets. Like, you know, in math, sometimes you might do like 2 times 3, like that. We don't do that in matrices. You just put them next to each other. Does that make sense? Unless you're talking about order of operations, right? Like if I was doing like A times BC, that's fine, right? Because it's like an order thing that you're talking about. But yeah, does that make sense? We don't put like, I guess the key takeaway is don't put like a little X or cross between them. Yeah.
You get lose marks on the test for it.
I don't think so. Not that kind. Something more major, probably. Like last time we were doing Gaussian elimination, and it was like spot all the errors. I think one of the errors is that they put equal signs between all the between each of the steps. That would probably lose you either half a mark or a mark. But yeah, so like a major notation error, we would take marks off. Something like this, don't worry about it. Any other questions? I just want to give this to you so that, like, you know, I mean, for 2 reasons, right? One is so that you have proper notation, because it's good to develop it early. Second reason is because if you're like on the internet and you see the cross somewhere, you see like A with a cross B, like XB, that you know that that's not matrix multiplication, that's something else, right? So like if you're like Googling stuff or something, that's a different thing. All right. So how do I do matrix multiplication? It's kind of this weird idea, right? So like what we do is we multiply the, I want to make sure I get this right, the rows of one thing by the columns of the next, right? So, and how do we sort of do that? Well, we do, so you have like a row, it has 3 numbers. You have a column that also has 3 numbers, right? So what we're doing is we're multiplying like the first with the first, the second with the second, the third with the third. Does that make sense? We're multiplying like as you go down, because they're going to be the same size. They have to be, right? That's what we checked. They have to be the same size. So first with the first, second with the second, third with the third. That gives you 3 numbers, right? So like 2 times 3 is 6, 6 times 4 is 24, 4 times 11 is 44. Then you add those numbers together, right? So the result, they're big numbers in this case, use a calculator, is 74. I'll let you double check that. Now, why am I writing it where I am? So when I'm looking at this problem, I took the first row and the first column. So 1, 1. So the result goes in position 1. My laptop shutting off, I think. Good, we're still good. Cool. Yeah, so first row, first column, it goes into position 1, 1. The first row, the first column of that output matrix. So let's do the next one. So we'll do 2 times 2 is 4, plus 6 times 10, plus 4 times 8, right? So we should get 96. So I did, or did I put that in the right spot? Yes, I did. 2 times 2, 6 times 10, 8 times 4. So it's first row, second column. So this is in the first row, second column. And we do the same thing with the second row here. So 1 times 3, 9 times 4, 7 times 11. Add the numbers together, you should get 116. If Google is right, I don't really know. I just took this question from the internet. So, and then 1 times 2 plus 9 times 10 plus 7 times 8 should give you 148. A good check is to make sure that the size that you ended up with is the same as the size that you expected to end up with, right? So remember we said 3 times 3 was, or sorry, the 3 columns here and the 3 rows of this matrix means that we can multiply, and then it's the outer 2 numbers that are your result. Also keep in mind those outer 2 numbers don't have to be the same, right? So you could have like a 4 by 3 multiplied by a 3 by 2, and your result is going to be 4 by 2, right? Cool. Just has to have those inner numbers matching, and the result is whatever's left. Cool. Any questions about matrix multiplication? Cool. What do I mean if I say, maybe we take this matrix here, 74, 96, 116, 148. What do I mean if I say this squared? Any guesses? Yeah.
Multiply it by another.
Yeah, so you multiply it by itself, right? Just do this matrix times itself. That'll give you the square. If I said cube, just do that 3 times, right? Doesn't, however many it is, right? That sort of leads to the question, what happens if I do put a negative number up there? What if I said like the power of -1? How do we even think about that, right? Because we know we can't divide matrices. That's not a thing that really exists. But there is an idea of inverse, yeah. So inverses are sort of more properly, they're defined as, so if I have 2 matrices, A and B, and if I multiply them together, and it gives me I, and I'll explain what I is in a second here. In a sense, I is kind of like the number 1, but for matrices. So I have 2 matrices, multiply them together, it gives me I, then the 2 matrices are inverses. So in other words, B is equal to A inverse. This is like saying A times A inverse equals I. And this should sort of be familiar from like normal multiplication of like numbers. If I had like X times 1 over X, that's going to equal 1, right? That's sort of the same thing here. So finding the inverse of a matrix is generally not easy. Like there's a procedure for it that you'll learn, but it's not like as easy as just like doing 1 divided by or something. Because of this weird matrix multiplication structure, right? So what is I? Maybe I should start there. I is always, it's called the identity matrix. It's always square, and it has 1s across the diagonal, and then 0s everywhere else. And when I say it's like 1, maybe this is something for you to try. If you multiply that matrix by any other matrix, it'll always give that, like if I did like any matrix A times I, it'll always give A back, right? And same thing the other way around. It's the same thing as like I times A. So it's kind of like 1, right? In the sense that like multiplying by it does nothing. Does that make sense? Cool. All right, so how do we find an inverse? Well, I'm not going to get too far into it, but there is a formula for the inverse of a 2 by 2 matrix. maybe I should write it out a bit differently. So say that I have a matrix A, B, C, and D, like this, right? Where A, B, C, and D are just some numbers. If I want to find its inverse, that's going to equal, should write this better, 1 over AD minus BC. So you just have to memorize this, sorry. 1 over AD minus BC. So you do this times this minus this times this. And then the matrix you multiply by is DA. So D and A swap places. And then B and C, they don't swap places, but they each get a negative sign. You get minus B minus C. Does that make sense? All good? Any questions about that? I know it's weird, yeah.
What would it look like?
That's a really good question. It does not in general follow this rule. So maybe I'll introduce this because it's kind of cool since you asked. You'll learn about this probably like next lecture, I'm assuming. But if it was a larger matrix, what you would do, like let's say that you wanted to find the inverse of, first off, to find an inverse, it has to be a square. Does anyone know why it has to be a square to have an inverse? Yeah.
Because you need to get the matrix and then squares.
Exactly, right? So like if it wasn't a square matrix, then when you multiplied it, you would end up with something that isn't square, and so it couldn't be I, right? So it has to be a square matrix. Maybe let's say you want to find the inverse of this. What you do is you write out the matrix, and then you put a bar, like a vertical bar, and then you write identity, the identity matrix on the other side. So you write 1, 0, 0, 0, 1, 0, 0, 0, 1, like that. I know it looks a little weird. It is a little weird. And then you use Gaussian elimination. So it feels weird, I know, but you're gonna do Gaussian elimination. So you're doing like different row operations. You're trying to get this whole side here to be 1, 1, 1 across the diagonals and zeros everywhere else. Once you get that, then whatever's left over on this side is the inverse. It's kind of cool. You'll do that, don't worry. I think that's next lecture. And next tutorial we'll cover it. Good question though. The other thing to say is that what happens if AD minus BC is 0? It's not invertible, right? There's a word for matrices that are not invertible. Does anyone know what it is? Just in case you see it. It's singular. So if it's not invertible, it's singular. It's like the opposite of invertible. In case you ever see that word on a test or something, they say, is this matrix singular? It means, is it not invertible? Does that make sense? Cool. All right. Any questions about anything before we move on? No? Cool. I'm going to stop